Hello people, welcome back to my channel. Hope you are enjoying the Python skill series so far. So we are currently doing a linear regression model. That is, we have so far created a linear regression model using the statsmodels.api library by using the OLS fit. So in the past couple two videos, what we did was, in the initial video we did exploratory data analysis EDA activity. Then following that, what our need is, that is our requirement is, we built a linear regression model for the cases, that is for the COVID prediction cases in India. And then we saw how our linear regression model performs based upon a statistical analysis. So we got the OLS test result summary, and from there, by reading the different values, we understood how this model is going to perform. Means how it will be productionized, or can it be productionized, or do we need to fine tune it even more. So now, since we have our regression model ready, now that what we need to do is we need to test it. So it's like the same with, like, if you have any product. So if any manufacturer of a company, say for example, if you are buying an iPhone, so what probably the Apple company will do is, before releasing it to production, or before it's being on a commercial basis, they do some test. So that consists of bend test, then different other kind of test, like they do waterproof test and so on. So that is for the convenience of the customer, like when they use it they should not face any problem, so they can trust and buy the product. So that's not with the phones, but with any of the real life products. Whenever you productionized, or like when you want to use it in your day to day life for any purpose, you do the uh, testing of that. And so with regression model, the model that we created, that is for even more significant testing. So that is basically for predicting the cases. So there should not be any errors when you uh, productionize it, or for predicting any new cases which is occurring. So for that, it has to follow certain assumptions that is laid out, that is the quality checks, in order to make it release to final deployment. So that's where you have four basic regression assumptions clause that we'll be seeing in this. So let's begin. So the very first thing that you need to do is, after you build a regression model, we need to find the residuals, means the errors that what you get, and you will see how the errors are, means they are less or more. Now since we know that our regression model performs better in this case, so what we do is, we run this lines of code. So these are some cells. So this is the A test that we have, that is, after partition we pass to this add constant method from the stats model, and this is what we have. And then we do the prediction, that is the B predicted. So we predict the results by using the results dot predict, and inside that we pass A test. So based upon the test results, you want to see how my model is predicting. So that is what this line of code is, or this particular cell is. And finally, you want to calculate the residual. So residual is calculated based upon the test value minus the predicted value. So whatever error you have, it can be positive or it can be negative. So you get the residual value. And if I print the residual value, it looks like this. So for different rows, the residual values are of, like, some are negative and some are positive. So this is my residual so far. Now this will not lay any statistical foundation, or any validation checks or marks for your model being accepted. So again, you want to give some gold standard thumb rules for making your model proof, like it can be used for production or it can be deployed. So for that, we have the very first assumption clause, that is no multicollinearity. So in statistics, as you can read from here, multicollinearity is a phenomenon in which one predictor variable in a multiple regression model can be linearly predicted from the others with a substantial degree of accuracy. So it is as simple. So there should not be multicollinearity when you build your linear regression model. So for that, we will use a method called as the variance inflation factor. So this is a very good website, that is statisticshow2.com. So I'm glad to introduce this website to you. So make sure you check this. So this particular website gives much of the insights regarding different statistical informations for doing your machine learning stuffs, or if you want to know or read more about statistics, I encourage you to visit this website to know much about this. So in this, they'll all mention what is multicollinearity and what is variance inflation factor, that is VIF. So it is primarily used in regression analysis, and we'll be basically using this. So the stats models.api library has the built-in functionality of determining if there is or if there are any multicollinearity present in your linear regression model which you have generated. So it is that useful library from where you can use it. That's why I've mentioned do not go with the sklearn library for model building. Use the stats models instead. So it has a wide variety of different other features which you can extend not only for model building but for testing how well your model is, or whether it passes the gold standards or not. Okay. So if you know what is the variance inflation factor is, and if you read from this, thumb rule of interpreting the variance inflation factor is, that is, one means it is not at all correlated. One means unit one, there is no decimals or there are no thousands, that is a single digit. Between 1 and 5, the variables are moderately correlated, and if it's greater than 5, that means they are very highly correlated. So exactly, if you see this, how large a VIF has to be before it causes issues is a subject of debate. But here they mention if your VIF value is significantly higher for regression results, then it is for a concern. So there are some suggestions from some authors or some data scientists, but we'll see for our model what is this thing and how we can do it. So here what I have is, I have a variable that is an instance, that is VIF. So to this I'm doing a list comprehension, and in this I have a method that is variance inflation factor. So you can read this. So this is a pop-up that comes. So this is the same thing that we have read from the blog. And to this, what I'm passing is a train dot values, that is the training values. So each of the training values it will take, and it will do the list comprehension for all the ranges which are there in this, and the shape it will take in this way. So it will be along the row, or if it is 0 it will be along the column. So you want everything in a row way, so you will get everything one after the other. And I am getting this, or I want this in a data frame format, and to this I am passing the VIF and VIF for each of the entries. And this is how the syntax is: a train dot columns dot t. You need not memorize this. This is like a fix, or if you want to like get to know what is this thing, and obviously many of the things you can't remember, but you should know where and how to use this. That is more important than getting to know what is the syntax. The syntax you can get itself from Google or Stack Overflow. Obviously if you type this and if you get some error, then it has the pop-up of searching to Stack Overflow. So that's not an issue, but you should know what to do, and if there are any some changes tomorrow in the future, what needs to be changed here. So that is more important. So if I run this, I can see the VIF for all my 35 different columns which I have, that is my predictor variables for my model. The new cases are for VIF, the VIF for new cases are 1.080, and this is exponential, means this is not 1 in number, just mind you, this is exponential e raised to plus 10. So 1.08 into e raised to plus 10. So that is exponential value, very high value. Similarly, for all the other predictor variables that you have, it is following a similar pattern. But if you look across, that if you look, that is for tests per case. So for here it is very low, that is 2.31, so that we can understand. And stringency index, it is somewhat not good, that is it's moderately correlated because it lies in between, no, it's highly correlated. Okay, so that's not an issue. The population, it is absolutely zero. Then population density, it is zero. For rest all values, for GDP per capita, it is zero, and rest all values, it's are exponential. Okay, hand washing facilities, it's again zero. So now what is the status for the exponential values? So if you just look onto this website and if you read here, sometimes a high VIF cause no cause for concern at all. If you get a very high VF by including products or powers from other variables in your regression like x and x square, if you have high VFs for dummy variables representing nominal variables with 3 or more categories, usually it's not a problem. So what the result we get from this regression analysis, that we can test, or we can ensure that there is no multicollinearity, or there are very less multicollinearity as per our benchmarks that we get from the variance inflation factor. So this is one of the first clause that your linear regression model should not break. So the first clause is satisfied, that is no multicollinearity. Next, we move on to the second assumption of linear regression, that there should be normality of residual. Now, residual is nothing but your errors, mean square errors or mean absolute errors. So, those kinds of errors, in that there should be normality, means it should be normally distributed. So normality is the assumption that the underlying residuals are normally distributed or approximately so. So there are different techniques by which you can understand whether your errors, whether they are normally distributed or not. So one such way to check whether your variables are normally distributed or they are following the normality of residual or not is by plotting a distance plot. So from SNS library, we have seen that we have uh, come across the distance plot that we have. So if you just pass on to the residual, and if you can look, there is this beautiful plot that you can see. I'll just zoom this out so that it fits onto the screen. Okay, so this is the plot how it looks like. It's a perfect, almost perfect Gaussian distribution, that is a normal distribution. So somewhere here you can see, but that's not an issue. One way, like assumption is like normal distribution is centered at 0. So that's how you can check this. So this peak, it somewhere relies around 0. So that means this is normally distributed, means there is a normality of residuals which is there in your linear regression model. And another way that you can do is something by using a probability plot. So we have not seen probability plot before. This is the first time that we are introducing this probability plot. So probability plot is called as PP plot or P plot. There are other measures also like quantile plots, Q plots also, but for this, for understanding your observed and actual results, how they are behaving, or are there any linear relationships with them, in order to understand or model that, or visually to understand that, you basically can go for a probability plot. One way is like you use the distance plot for residuals, that is one option. This is another option. If you are not satisfied with that, then you can go for the probability plot. To the probability plot, this method resides inside the stats model, that is the sn.prop plot, and to this you pass the residuals, and then you have the fit is equal to true. I'll explain what this fit is equal to true after I plot this. Then you have the figure. So what basically I want is, I have the distribution on a canvas, and onto this canvas I'll pass a 45-degree line. So if you know, for linear regression, you have the line that should pass through origin, and it will be a 45-degree line, that is tan 45 is equal to 1. So with that notion, I have this line is equal to 45, and this is the chart name or the diagram name that you want to put, that is plt.title qq plot. So that plot name is, or the name of the chart or graph will be residuals of OLS fit. And finally I'll be doing a plt.show, and this is how my probability plot basically looks like. Okay, so on the x-axis you can see the theoretical quantiles, and on the y-axis you can see the sample quantiles. So that is the actual and the observed values. And right from the zero, right from the center, there is a 45-degree line that is passing through all of the points. So most of the points uh, are covered in this particular line. So this is a 45-degree line, regression line, that you are passing through this. So this states that there exists normality of residuals among your data points or in your linear regression model. Now that I said, like if you change this fit is equal to true, and if you put to fit is equal to false, what will happen is your diagram will look something like this. So your line will be uh, starting from or passing through the 0 or 45-degree line, but your points won't be fitted. So in order to correct this, you basically do the fit. So that is the small difference that I want to make into your consideration, that is, you have to put fit is equal to true. And this was the second option to check for the normality of residuals for the errors. And one small fix is like, if the residuals don't sum up to much of the errors, means their error value should be less, so the mean of this residual should also be less. So if that is the case, then from numpy we have a method that is np.mean, and to this I'm passing the residual, and if I run this, you can see the residual value is negative 0.11. That means the model is good. Also there exists normality of residuals, means the error should not be very explosive, or it should not be very high. Okay, so now that we saw the second regression assumption clause, we now move to the third assumption clause, that is the homoscedasticity. So homoscedasticity describes a situation in which the error term, that is the noise or the random disturbance in the relationship between the independent variables and the dependent variables, that is the y and the x, is the same across all the independent variables. So it's like, in a layman language, if I want to describe what is homoscedasticity is, the distribution of the error should be uniform. There should not be any pattern that should be forming, like it should not be monotonically increasing or monotonically decreasing, or there should not be any cone shaped distributions or like that. So it is as simple as that. So let's see if we get any patterns. We should not ideally get any patterns, and this is the syntax for plotting the homoscedasticity. And the way that I plot is by using the subplots, and the figure size that I'm putting is 10 by 10. And these are the basic syntax that you would use to plot or check for homoscedasticity. So this is the plot that I get. So you can see the points, they are lying in some fashion, but you don't pretty much understand, like there are some relationship between these variables. They are somewhat distributed, means there are no patterns that is observed. So that means like this linear regression model that you created is not breaking the homoscedasticity assumption. So if you want to get more information about this plots and from where I plotted this is the website. That is the official website for statsmodels.graphics, and from this you have golfplots.propplot. So I plotted all these things from this particular website. So this gives a comprehensive idea of all the statistical packages and all the coding stuffs. So from this you can actually read and actually code different plots that you want to get. So they explain each of the things, like how you can do a QQ plot, that is a quantile plot. Then from here only I just plotted the probability plot by following all these steps. Then you have the empirical cumulative distribution. So when you do the model building, you should be able to know what are the statistics or what is going behind that. So that is most important. The coding part you can do googling and search on Stack Overflow and you can do this. But under the hood, what's happening, that's more important. So you can visit this website. You can understand how the things are going around, what are the different parameters, and you can learn basically all of them. So I'll just put the link in the description. So whenever you get the time, you can visit this. So that we saw our linear regression model satisfies the homoscedasticity. We move on to the final clause that our linear regression model should satisfy, that is there should not be autocorrelation of residuals. So autocorrelation basically refers to the degree of correlation between the values of the same variable across different observations in the data. So it is the same, so you can understand from what the thing is actually seen. So if I run this, and this is the same plot from where I get this, that is smt.graphics plot ACF, that is the autocorrelation for residuals. And to this I'm passing my residual, and there are some lags and alpha value. And if I do a ACF.show, this is how this basically looks like. So this is the autocorrelation plot for which your linear regression model should satisfy, or it should not break this. Now what makes it break? So here on this you can see a very blue band or a blue border which you can see, and this thing what you can see which is outside this blue band, that is every variable that is correlated to itself. So that you cannot do anything with that. So each and every variable to itself is very much highly correlated. So if I ask you how much do you love yourself, so you say I love myself very much. So the same thing, every variable itself is very highly correlated, so that's why this value is very high, that is to 1. But all the other variables, like one independent variable and one dependent variable, they should not have any correlation between them. So that's why you can see that it's not going outside this band or outside this border, everything is lying in between this. So whatever parameters we have taken, they have put in a different scale or different buckets, and accordingly they are following this in different ranges. So if all these things are in place and it's not breaking any of the assumptions for linear regression, that means that whatever you have done, or your linear regression model, from the summary results and also from these assumptions, you can say that your model is ready to deploy. So next video or henceforth what we'll be doing is we will be uh, building an application, small application on Flask, by which you can deploy this on some cloud services. So if you have any doubts or questions regarding this particular video, or if you have not understood any video part or portion, so make sure that you ask in the comment section. And if you are new to this channel, please consider subscribing, and thank you very much for watching this video.